So we are here to learn about metallurgy. So metals, as we've learnt, that they have varied reactivity and hence there is a reactivity series. Some metals are not reactive at all. So those metals are known as noble metals. Copper, silver, gold, platinum, these are termed as noble metals. Though copper is somewhat reactive and as well as unreactive. So the metals which are less reactive or non-reactive, the noble metals, they are found in their native state, means element state in nature, in the earth's crust, whereas the metals which are reactive, they are found in their compound or combined state. So copper has the benefit of being in the native state as well as combined state. Whenever in the earth's crust these metals, non-metals or the inorganic substances, they are found in the earth's crust. So these naturally occurring inorganic substances found in earth's crust are termed as minerals. Minerals could be elements, minerals could be compounds also. If these are compounds, they are mostly due to the attack or action of air on the metals. So either they are found in their oxide state in nature, or in the carbonate state or sulfide states, or in the seawater the metals are found in their halide forms. Like sodium chloride is a halide, magnesium bromide, magnesium chloride, the fluorides, these are all halides. Now we are looking at how do we extract a metal from its mineral. So those minerals from which metals can be extracted profitably and efficiently are termed as ores. So all ores are minerals, but all minerals are not necessarily ores. When the metals are mined, the ores are mined from the earth's crust, they are generally containing earthy impurities of silica, clay particles, sand particles, rock particles, and these are the impurities are termed as gangue. If a certain ore has high quantities of gangue, it is termed as a low grade ore. If the ore has low quantity of gangue, then it is termed as high grade ore. So in the process of extraction of metals, the first importance is of removing these impurities. So let's look at the steps of extraction, and this process of extracting a metal from its ore profitably, efficiently is termed as metallurgy. So metallurgy is defined as the process of obtaining a metal from its ore efficiently and profitably. Extraction of metal takes place in certain steps. The metallurgy has certain steps. So first step always is that you grind the ore to have it in the powdered form so that the impurities can be efficiently removed. So this crushed or ground ore is concentrated, or this step is known as enrichment of ore, which particularly is a process of converting a low grade ore into a high grade ore by removing the impurities. There are different methods used to separate impurities. If it is a sulfide ore without the impurities, then you use froth flotation process. If it's an oxide ore or a carbonate ore with high density, and obviously there are the impurities. So in comparison to earthy impurities, the density of the ore is higher. Then we use hydraulic washing as the method of enrichment or concentration. If it is a non-magnetic ore with if it is a magnetic ore with earthy impurities, that is non-magnetic impurities, magnetic separation is applied. And in case of ores like alumina or bauxite ore of aluminium, we apply the process of chemical separation for concentration. There are different methods applicable for different kinds of ores. So concentration of ore is particularly removal of impurities. After the concentration of ore, the other different steps depend upon the reactivity of metal. If it's a high reactivity metal, then it is simply obtained by electrolysis of the molten ore, and that happens in the case of bauxite ore of aluminium. Aluminium is a high reactivity metal, so you after carrying it through the process of chemical separation, that's for concentration. It is obtained in the form of alumina, and that is aluminium oxide. So this molten aluminium oxide is electrolyzed to obtain metal on the cathode. Whereas if it is a metal of medium reactivity, there are probabilities of it being in the form of an oxide, carbonate or sulfide. If it's an oxide, then it would be directly processed further, and if it is a carbonate or a sulfide, it needs to be converted into oxide, because it's easier or it is more profitable and efficient to obtain a metal from its oxide instead of from sulfide or carbonate. So first the carbonate and the sulfide are converted to oxides. So how do we convert the carbonate into oxide? So this is done by heating the carbonate ore in absence of air or in sufficient air, and this process is called as calcination, and as a result of calcination you obtain the oxide from the carbonate. Let us look at an example. So suppose you had zinc carbonate. When it is heated strongly in the absence of air, you obtain zinc oxide and carbon dioxide is produced. Then if it was a sulfide ore, then it would be, let us look at the FeS. It's to be heated strongly in the presence of air, and you obtain iron oxide and sulfur dioxide. So that's how this process is known as calcination. This process is known as roasting. So through either roasting or calcination, depending upon what kind of ore you have, you convert the ore into the oxide, and then the oxide of the metal is reduced into the metal, and then further the metal is refined to obtain high purity metal. If metal is of low reactivity, then the sulfide ore that it is present in is roasted, and then the roasting will result into formation of metal oxide. That metal oxide is reduced to metal, and then metal is refined. Extraction of metals. We are elaborating the extraction of metals of low reactivity in activity series. So metals which are low in activity series can be reduced to metals by heating in presence of air. We've looked at this. And mercury is obtained from its cinnabar ore, and by heating it in presence of oxygen, it converts the cinnabar ore into mercuric oxide, and this mercuric oxide on further heating breaks into mercury and oxygen gas is released. Copper is also obtained in the similar manner. Copper is found as copper pyrites in earth's crust, and this copper sulfide, when it is heated in the presence of air, first it gets roasted to cuprous oxide, and this cuprous oxide in the presence of cuprous sulfide, that was the ore initially, and it will reduce by itself into the copper metal sulfur dioxide. Now let us look at the process of calcination. This is an example of roasting, and we'll look at the process of calcination next. Now metals in the middle of the reactivity series. Metals in the middle of the reactivity series like zinc, iron, lead are found as their oxides, sulfides or carbonates. We have already looked at the roasting, and here the roasting of the zinc sulfide to produce zinc oxide and sulfur dioxide. If it was the zinc carbonate, that is the carbonate ore, it's heated strongly in the absence of air, that's calcination process, and you obtain zinc oxide and carbon dioxide. So when you compare roasting and calcination, this is calcination and this is roasting. Calcination is applicable for carbonate ores, roasting is applicable for sulfide ores. Calcination is heating strongly in the absence of air and sufficient air. Roasting is heating strongly in the presence of air or sufficient supply of air. Then the byproduct in case of calcination is carbon dioxide, whereas the byproduct in case of roasting is sulfur dioxide. Calcination is the process of decomposition, whereas roasting is the process of oxidation of the ore. So these are the various differences between roasting and calcination. So here what you look at is, if the metal is in the middle of the reactivity series, after you obtain the oxide, the metal oxide is reduced with the help of a reducing agent. Mostly the reducing agent is carbon, and this process is known as smelting. When you use carbon as a reducing agent, you obtain the metal and you obtain the carbon monoxide. And this carbon monoxide, since it's very reactive, it will further aid the reduction of metal oxide, and ultimately it will produce the metal and carbon dioxide. This process is known as smelting. Sometimes, in order to reduce the metal, reactive metals like aluminium are also used. So you look at this example where manganese dioxide is being reduced with the help of aluminium metal. So it produces manganese metal and aluminium oxide is formed, and a lot of heat is released. And this reaction, since a lot of heat is released in the process, are known as thermit reactions. So to join the broken railway tracks, we use the reaction of iron oxide with aluminium. So if the ferric oxide is reduced with the help of aluminium, you obtain the molten iron metal and you obtain the aluminium oxide, and heat is released. This heat is actually leading to melting of this metal, and this molten metal can be used to join the broken railway tracks. This picture shows you how thermit reaction is used to join the broken railway tracks, where you cannot perform welding through the electric process. Here this thermit process is very successful. So as a result of the 3 steps of metallurgy that we have looked at, the concentration, that is enrichment, roasting or calcination if that was required, and reduction, ultimately you obtain the metal in the form of extracted metal from ore. And this metal is not very pure, it still has probability of having impurities present in it. So in order to remove those impurities, further refining of metal is required. There are various methods applied for refining, but one of the most common and most effective method is electrolytic refining method. Here in this slide, we are looking at the electrolytic reduction if the metal was a high reactivity metal. So for the low reactivity metal, heat alone was applicable, that within the process of roasting or calcination, the oxide also gets reduced to the metal. The low reactivity metals were treated that way. The middle reactivity metals, they were smelted or thermit process was applicable. If the metal is of high reactivity, then the metal oxides are electrically reduced. Electrolytic reduction method is applied, which is done in the case of sodium metal, which is done in the case of alumina. That is what we've discussed. We look at the refining of metal here. So copper metal, which is obtained as a result of metallurgy, does not have high purity, and hence the electrolytic refining method is applied. For that, an electrolytic cell is used. I'll erase the board and we'll look at the electrolytic refining of copper. Electrolytic refining of copper. For every electrolytic process, you need an electrolytic cell, and you need 2 electrodes and an electrolyte. The electrolyte in this case would be the salt solution of a copper salt. Here we take copper sulfate solution, which will produce the copper ions and the sulfate ions in the solution. You need 2 electrodes. So here the electrodes that we choose are that we use a thick block or the metal that is obtained as a result of metallurgy, that is impure copper, as anode. So it is connected with the battery, positive terminal of the battery, whereas a thin strip of pure copper, this is to be taken as a resource here. So a thin strip of copper metal is used as cathode, which is the negative electrode. Be very careful about the terminals of the cell or the battery. So what happens here, due to the electric current supply, the cathode will attain a negative charge and will attract the positively charged copper ions. So let's look at what reaction happens at cathode. The copper ions reach here, obtain electrons from the outer circuit and will turn into copper metal, and this copper metal deposits over the electrode. What happens at anode is the copper metal from the anode will lose electrons and will turn into copper ions. These copper ions from the anode will migrate to the solution, and from the solution they will migrate to the cathode, and this process continues till the entire copper metal is transferred from the anode to the cathode. As a result, the impurities which were present in this block will fall down and they'll collect here as anode mud. And surprisingly, interestingly, this anode mud contains traces of gold and silver also. So this is a process of oxidation at anode, since loss of electrons, and process of reduction at cathode, since there is gain of electrons. So in this process we obtain copper metal of 99.98 purity. So we look at the next topic of the chapter, corrosion. Corrosion we have discussed earlier also. When the metals are attacked by moist air, there would be formation of oxides, carbonates, sulfides on the surface of metals, and the metal appears dull. Sometimes, as in the case of iron, this oxidation of metal surface leads to a wastage of metal from the surface. Rusting of iron becomes a threat to a nation's economy even, because the iron is attacked by moist air and it rusts. The rust formed there is a flaky reddish brown layer which would shed off and allows the further attack of metal by the moist air, and the process continues till the iron object becomes weak and it rather fractures and it breaks also. That leads to falling of buildings, bridges, etc. So we need alloys of high grade in order to build constructions and make buildings or bridges, etc. Let's look at how the rusting takes place. What all factors are important in rusting? So here 3 boiling tubes are taken, which are tagged as 1, 2 and 3. In the first one, there is anhydrous calcium chloride kept, and an iron nail is put into it, and the boiling tube is corked. In the second case, boiled distilled water is taken, and iron nail is dipped in this one also, and here the drop of oil is put on the surface of the water, and again the boiling tube is corked so that no air can enter from outside. So then the third case, there is some water taken and iron nail is dipped, and this boiling tube is also corked. When this setup is stored for 2-3 days, what we observe in the first case, rusting does not take place. What conclusion can we draw from here is that there was air but there was no moisture or no water here, so rusting did not take place in the absence of moisture. In the second case, there was water but there was no air, and rusting does not take place in the second case also. That leads to the conclusion that rusting requires air also. In the third case, there is availability of both air and water, and this iron nail rust. So this activity leads to the conclusion that rusting requires both air and water. So how do we prevent corrosion? To prevent corrosion, we apply oil or grease. In case of your bicycle chains, the grease. The machines, the sewing machines, they are lubricated by using machine oil to prevent wear and tear. painting of window frames and all happens because the paint will prevent contact of metal with the air, and that also prevents rusting or corrosion of metal. Galvanization, which is the process of dipping the cleansed iron objects into molten zinc, and hence it develops a layer of zinc. Zinc in presence of iron will form an electrochemical cell. So if the zinc surface or zinc coating gets scratched at some point, even then in the presence of moist air it will form an electrochemical cell, and it will not let the iron rust as long as the zinc coating is available around it. Tinning is another method of preventing corrosion, particularly rusting. We have electroplating and then alloying. Let's look at the composition of a few alloys here. Steel is an alloy of iron carbon. Stainless steel, however, is an alloy containing iron carbon, but in addition it contains cobalt and nickel also. Brass is an alloy of copper with zinc. Bronze is an alloy of copper with tin. So solder is an alloy of lead and tin. These alloys have unique properties, and their properties, physical properties, are different from that of the metals they are made from. And we conclude the lesson here. Thank you so much.